Hi, I'm Leah Perlmutter, and I work with Maya Chakmak at the Human-Centered Robotics Lab. This work has 3 contributions. First, we present a new situated language understanding system. Second, we introduce visualization-based transparency. And third, we evaluate the effects of visual transparency in an empirical user study. Our system understands commands delivered by a user through a combination of speech and pointing gestures. The robot is situated in a model living room containing furniture, household objects, and picture frames. The user is seated facing the scene. We use 2 Kinect sensors to gather depth images from the environment. The first Kinect faces the scene and is used for object detection with tools from Point Cloud Library. The second Kinect faces the user and is used to detect pointing gestures. The user wears a microphone and delivers a command through a combination of speech and pointing. The system enables objects to be referenced in a variety of different ways. Suppose this user wanted to reference the red cup. She could say, "Pick up the red cup," or "Pick up the cup that's on the table," or she could point at the cup and say, "Pick up that object." The system has the means to recognize all these types of references. Here's an example of some dialogue.
What should I do next?
Pick up that object.
You would like me to pick up that red dish. Is that correct?
No.
What should I do next?
Pick up that object.
You would like me to pick up that red cup. Is that correct?
Yes.
What
As you can see, there's room for misinterpretation of the user's input. This is the case for any complex system, and there needs to be a way for the user to correct it. That's where transparency comes in. Transparency is where the robot reflects its understanding back to the user. As in related work, we do that with a verbal feedback step.
You would like me to pick up that red dish.
In this example, the robot used speech and gaze to indicate the target object. In some cases, it also uses pointing. These mechanisms, speech, gaze, and pointing, are human-like, or natural transparency mechanisms. We introduce a new transparency mechanism in the form of graphical visualizations displayed on a screen. Visualization-based transparency is our second contribution in this work. Here's what the visualization looks like. First, the screen displays a representation of the robot's environment, revealing which surfaces and objects the robot can detect. Next, it displays 2 pointing cursors, one for each hand, exposing where the robot thinks the user is pointing in real time. It highlights surfaces and objects as the user points at them. It also displays the user's last utterance as detected by the speech recognizer. Here, real-time feedback from the visualization helps the user to make an accurate pointing gesture. The visualization can also be displayed through a virtual reality headset. With the VR display, the user points by centering their gaze on the pointing target. We conducted a user study to test the effects of visualization-based transparency. In the baseline, we used only natural transparency. In each of the experimental conditions, we added visualization-based transparency with one of our devices, screen or Oculus. We found that visual transparency improves task performance. Users spoke fewer words and took fewer attempts to convey a command with visual transparency. Visual transparency also changes user behavior. For instance, people used pointing more often in the screen and VR conditions. In the visualizations, the robot displays numeric labels for objects and surfaces. Another behavioral change was that people used these labels to refer to objects. For example, pick up object 72, place it on 5, and clean surface number 6. For more detail on our results, please visit us at the interactive session.